Introduction. Can everyone see my screen?
Yes, we can. I think
Okay, great.
I can.
So good afternoon all. My name is Caryn Biebuyck and I'm an honors graduate from Stellenbosch University. Last year during my honors degree, I was 1/3 of a research team tasked with using Mitre's attack framework in some research capacity. After investigating the topic and the cybersecurity landscape in general, our question quickly became, how can one share threat intelligence in a meaningful manner? So, what is Mitre's attack framework? The attack framework is a global knowledge base of adversary tactics and techniques, which have been curated from real-world experiences. Mitre's website features matrices pertaining to enterprise, mobile, and industrial control systems specifically. We chose to focus our application within the industrial control system domain, as their increasing reliance on computerized information systems and dynamic nature has significantly increased their security risks, as well as the domain being relatively underdeveloped in terms of information sharing. Attack for ICS describes the actions an adversary may take while operating within an ICS network. The Navigator matrix visually aligns individual techniques which are associated with specific procedures or software under the tactics in which they apply. Some procedures span more than one technique because they can be used for different purposes. Each technique or software is also associated with hardware assets and a level within the Purdue model, which is famous for describing the logical architectures of ICS networks. We wanted to represent the information made available by Mitre in a way that would allow practitioners to easily identify similar adversary actions within their own systems, as well as likely future actions in order to reduce the risk of ICS components being compromised via improved detection and response times. We were able to do this using a combination of formal concept analysis and later the development of an ontology. Formal concept analysis, or FCA, is a philosophy of data analysis that classifies datasets into conceptual structures. Entities of interest are used to derive a concept lattice, which can be used to extract ontological classes of terms, a hierarchical ordering of concepts, as well as implications and associations between concepts. By encoding the known adversary techniques and associated software into a formal concept lattice, FCA visualization and analysis could be applied to reveal deeper associations between the relevant software. To create this lattice, we first extracted a dataset of adversary techniques and associated software procedures and created a formal context using a cross table in Connex. Techniques were mapped as objects and software as attributes. In the lattice in the slide, upward edges between the nodes encode logical implications, which enables one to immediately derive more information about which techniques and softwares are likely to be used in combination, allowing for faster mitigations of attacks. Next, using the Duquin-Giges solver, sorry if I've butchered that pronunciation, but the set of implications and association rules can be calculated within the formal context. In this table in the slides, these implications stand to reveal which software are likely to be introduced given the presence of other software and at what confidence, enabling one to determine the priority of attack techniques on the basis of software linkages. We categorize the software implications into probability groups according to whether they are low confidence, medium confidence, or high confidence. As an example, the solver shows that in implication 15, the presence of software S009 and S0013, resulting in the presence of S0010, has a confidence of association value 1, which means there's a high probability that the techniques used by S009 and S0013 will also be present by S0010. This shows that more attention would need to be paid to associations that have high probability values. Next, the results of the FCA exploration were encoded into an ontology. An ontology in its simplest form is an explicit specification of conceptualization, meaning ontology explains the concepts within a domain of interest as well as the relationships between those concepts in a formal language. By developing the ontology using OWL2DL via Protégé, machine interpretation and semantic web reasoning was enabled. Moreover, the query capability afforded by the ontology can assist practitioners in faster mitigated responses to cyber attacks. The steps followed to develop the ontology included clarifying the domain concepts that the ontology must cover, encoding the relevant classes to the ontology, populating the ontology with instances, specifying instance relations, and finally, creating queries to test whether the ontology would be useful for revealing knowledge about adversary behavior. Given the probabilistic aspect of the software implications, we specifically chose to implement implications as individuals rather than as general class axioms, due to the fact that general class axioms generated invalid inferences. In order to demonstrate how the ontology can be used, we'll now look at a high-level example of how queries can be used in a hypothetical situation. Imagine a security practitioner suspects a data historian asset is compromised within their system. The practitioner would first want to know which software would be involved in the attack, which can be identified using the query on screen. The query returns 14 software respectively. Now let's presume the practitioner is only concerned about implications with a high probability. Accordingly, this new query would return 12 software instances, all of high probability. The practitioner could then use a variety of queries to trace the implication conclusions of these software and ultimately identify and intervene hardware components that are likely to be targeted next. To conclude, by using a combination of FCA and ontology engineering, we were able to produce a meaningful representation of the threat information collected by Mitre. We were also able to challenge specialists to consider how they should defend against ICS manipulations specifically. Thank you. So yeah, are there any questions?
Thanks, Caryn. I don't see any hand at the moment. Let me see if I can check the chat. Any questions? I might have a question. What would your next steps be if you were to take this further?
Well, I know Mitre has recently updated their information available to the ICS matrix specifically. So I think it would maybe trying to be expanding the ontology to include that information. I know another thing is with the FCA, there's been research into like incremental constructions of lattices. So maybe if you could like automate that process, that could be cool as well. But yeah, I see this project. I'm not too familiar with how ontologies work with like system integration, but I think it could be cool if this could get to a place where your system could automatically know that this component is going to be vulnerable next. So put in automatic mitigations almost.
Okay, yeah, thank you very much. I'll give one more moment for questions, although I don't see any. All right, thank you very much for that presentation.
Yeah, thank you.
Okay, so I guess then I'm chairing the next